There we go. Excellent. All right. Welcome, everyone. This week's lecture was going to be the beginning of our section 4, our fourth section in the course, the last section that we're going to have in the course. And this section is all about actually practically using statistical inference for various goals, for our science and basically the whole purpose in which we're here. And so giving sort of a general summary of why we take these sorts of statistics courses, there's sorts of 4 things that I kind of want you to learn as part of this process, as part of this lecture series. So the first of which is being able to understand complex data. So that was section 1. The second is to understand probability and the probabilistic nature of experiments. That was section 2. The third section is having access or giving you access to the tools that you need in order to estimate models given a data set. So that was when we started talking about Bayesian statistics and MCMC. And then the last step is understanding how to interpret models and interpret results and do accurate statistical inference. And this is arguably the most important part, but obviously you can't do section 4 without first having an understanding of 1, 2, and 3. So this is where we've been building to for the entirety of this course. And I think this is probably part of the, some of the most interesting content in this course. Now, one of the problems that we have when we do statistical inference, one of the conundrums that we run into is that, as we stated when we first started this course, 10 weeks ago, we essentially never had access to the full gambit of all possible observations that we could have. Instead, what we always have, or we generally have, is a subset of all possible observations that we call the sample that we have, and we have to try and do some sort of statistical inference with that sample. And so, because there's always going to be different ways that particles bounce off one another, there's always going to be different galaxies to observe, we're always going to be trying to infer a parameter theta from an incomplete sample of observations. And those estimates that we get of theta are themselves going to be random variables. So regardless of what experiment we're doing, regardless of the application, whether we're working in astronomy, physics, biology, or any sort of model optimization, we're always going to be trying to estimate something from a finite series of observations, and those finite series of observations have some variance just because they are a finite series of observations. And so it's natural to ask the question, how significant is the estimated value of my model given the fact that I know that I'm working with an incomplete set of observations? So what we want to say is we want to measure whether or not a variable has a significant difference or a significant agreement with regards to a particular model, given the expected fluctuations that we have from a random variable, and that random variable being a sample of observations. One of the simplest ways to understand why this is just to actually think of a really practical example. So let's say that we have a theory. Our theory is that the average height of all human beings is 184 centimeters. Okay, and we want to know whether or not that estimate is accurate, or whether or not our hypothesis is borne out by the data. Now, obviously, we can't go around and measure every single human's height on the planet. Firstly, because it's just unfeasible to do so. But secondly, even if you could do it, by the time you got to the last person, the first person will have grown, right? So it's an unfeasible job. And so therefore, what you have to do is you have to take a sample of humans, you measure their heights, and you use those heights as an estimate of the truth, of the underlying true human height that you don't. What we then want to do is we want to say, how likely is it, given the sample of observations that we've observed, that our hypothesis is true? Okay, and and the crucial thing is that we know that the sample value, the average height that we measure from our sample is going to change depending on which sample we take, right? If we accidentally take a particularly pathological sample, then we're going to end up with an estimate of the average height that's very, very small or very, very tall, right? And conversely, if you take something that is essentially a sparse sampling of all human heights, then you might get something that's reasonably close, reasonably accurate. And so you want to ask the question, how significant is the difference between my hypothesis and the data that I observe, given that I expect the sample to be to have variance in it because of the finiteness of it. One way you can actually determine whether or not your hypothesis is correct is by generating some interval, like the credible interval that we spoke about during our Bayesian probability discussion. And we can say, I expect that the true value of my parameter, in this case, the height of all humans, is going to sit within some particular range, within some particular confidence, within some probability. So for example, 95% of the time, my truth is going to be encompassed by this credible interval. And so you can construct that interval, and you can find that, so we say we do that, we construct an interval, and we find that our value of 84 centimeters is outside of that interval. So what does that mean? What does it mean if the value that we measure is outside of that interval? Well, the first thing it could mean is that the value of the average human height being 184 centimeters is unlikely to be correct. That's the first possible conclusion that you could draw. But there is another conclusion that you could draw. And that other conclusion that you could draw is that we just got very unlucky with the sample that we drew, right? And that in fact, the hypothesis is true, we were just unlucky. That procedure for determining whether or not the data contradicts a particular hypothesis by saying whether or not it is outside of a confidence region is the thing that we're going to focus on today. And so that sort of begs the question, why do we actually care about whether it contradicts our hypothesis rather than whether it agrees with our hypothesis? And this is going to lead us into the first little poll that I want us to do for today. So the first question is, well, the first thing I want to get your opinion on is how much evidence is required to prove that a hypothesis, to prove that my hypothesis, which is that I have some theories, the average height is 184 centimeters. How much evidence do I require before I can prove that that hypothesis is correct? So it's a difficult question, right? So have a go, put in your gut instinct of whether or not, can I say that my experiment or my hypothesis is proved if I have one observation that agrees with my hypothesis? Do I need 5? Do I need 100? Do I need 10,000? So effectively, do I need an infinite number? Right? So these are the different things. The other way to formulate this question, so we'll just wait a minute until we have a few responses. The other way to formulate this question is what we're going to ask next. All right, we've got sort of half the number of people there. Wait, maybe just another minute. All right, let's have a look at the results. Okay, so quite rightly, the majority of you are landing in the many observations, landing in the point of you need to have many experiments that agree with your hypothesis before you can prove the hypothesis is true. Interestingly, there's a peak at 100 rather than the peak at 10,000, but we'll see about that in a second. So let me ask this question slightly differently. Instead of asking the question, how much evidence does it take to prove that my hypothesis that a theory is correct is true, so to prove my hypothesis is true, What about the opposite of that statement? How many experiments do I need to prove that an observation is to prove that a theory is wrong? How many experiments need to contradict the theory before we assume that that theory is no longer any good? Okay, so let me clear these results and we can start again. So now, instead of to prove that my theory is correct, I want to say to disprove my theory. So how many observations does it take for us to disprove a theory? Now, I probably should have said this at the beginning, but I'm going to say it now. Let's assume for the moment that all experiments are perfect, that the only thing that goes into an experiment is random noise. And that, experiments are decisive, so that they're a binary outcome. There's no ambiguity. They are either, yes, this is true, or no, this is false. So given those two conditions, that there is no experimental error, systematic error, but just random noise, and that the experiments are decisive, it's very, very difficult to maintain a hypothesis that a theory is correct if you have any evidence to the contrary. However, an infinite number of observations would be required for you to say with 100% certainty that this theory is correct, because all it takes is the next observation to disagree with the theory, and all of a sudden you're back to square one, right? So I would say, I would say that no amount of evidence can ever give you absolute certainty that a hypothesis is true. It can only fail to show you that the hypothesis is not true, which is to say that you always have to take more observations to create greater confidence. You can never be 100% certain about anything. However, it only takes one piece of evidence to disprove a hypothesis, right? And because of that disparity, it makes sense for us to focus on whether or not a hypothesis contradicts the data rather than whether or not it agrees with the data. Because as I said, if you need an infinite number of agreements in order to think that you are confident, but only one disagreement, then it makes sense to focus on the disagreements. And so this is why we tend to focus on whether or not two observations and hypotheses are in conflict with one another, whether they contradict one another, rather than whether or not they agree with one another. This then leads us into the concept of significance. And this is the overwhelming sort of umbrella under which we're going to be talking about what we're going to be talking about for this lecture. So given that we have some sample of human heights, we want to assess the significance of our evidence with respect to a particular hypothesis. Now, our particular hypothesis is that the true average height of humans is 184 centimeters, and we take some data and we calculate the average of that data, the average height of people in that sample, and we then want to get an idea of how significant the difference between our data and our hypothesis is. Now, one of the ways we can do this is, as I said, we take n humans and we calculate the mean of those heights, and then we ask the question, given a sample of n humans, how often should we observe an average height that is as extreme as the one which we observe, if the hypothesis is true? Now, so our hypothesis is that the population mean is this thing, mu hat, and we observe some mean x bar, and given our sample of n observations. We can then approximate the variance on this mu hat by using the sample variance of our sample, which is just S squared, stuff we've already covered earlier in the course. And we can use that to get an estimate on the standard error of mu hat, which is just S over square root of n. Okay, standard error on the mean, but using the sample variance instead of the population variance here. We can then use these values that we just determined to create a statistic, which we're going to call the test statistic. And the test statistic here is x bar minus mu hat, sorry, missing a hat, S divided by the square root of n. Now, you might recall from our second section, our lecture on probability distributions, that this t statistic here is the, well, it's called the t statistic, and it's related to the student t distribution. And we know that that distribution is analytic. So we know the PDF of that thing, and it means that we can calculate the probability of observing a sample of data x bar with, a sample of data with mean x bar, given the values of mu, n, and s. And that follows a student t distribution. And so we can integrate this thing, this student t distribution, between the values of minus t and t. Right? And that gives us this value f. Now, what does f describe? We've essentially constructed, and I'm going to draw something here. We've essentially constructed a distribution, student t distribution looks something like this, as you'll remember. And we've said, what is the probability, or what is rather the integral of this function from minus the absolute value of t to the absolute value of t? Okay, and that's going to be some value between 0 and 1, because this is a PDF. This is t on the x-axis. And so we'll call that t hat to make it a bit clearer. And this is going to be some value between 0 and 1. Okay, because it's a probability distribution. Nu here is just the degrees of freedom, which you know we discussed is just n minus 1. Cool. If we pick a value of t hat that is very, very large, very, very positive, or also very, very negative, right? Then the integral of this thing is going to be basically f is approximately equal to 1, right? Because you're essentially saying, what is the integral of this distribution from almost minus infinity to almost infinity? And it's a PDF, so it has to be equal to 1. What that means is that essentially every single random sample that we generate, which has a true mean mu hat, will lie within minus the absolute value of t to plus the absolute value of t. Right? If this f is near 1, every single sample that we could possibly generate from our hypothesis would have a value that is smaller than the t which we observe. If that's the case, then the probability of observing our value of t by random fluctuations is very, very small. And so it's convenient to formulate this number in terms of that 1 minus f, which is what we call the p-value. And I am sure that the overwhelming majority of you have heard of this term p-value before. And it is my opinion that the p-value is quite easily the most misused, misunderstood, misrepresented thing in the entirety of statistics. Okay, so we're going to spend today learning about abusing the p-value. And that's exactly what we're going to be talking about. We're going to be talking about the p-value, bad statistics, and what the p-value does and does not do for you. So what does the p-value mean? What is the p-value? What does it tell you? The p-value represents the fraction of samples that would produce a test statistic that is as extreme as the one you observed, given that the proposed hypothesis, which is generally the null hypothesis, which means that the hypothesis is that there is no effect. The p-value is the fraction of samples that produce a test statistic that is as extreme as the one you observe, given that the proposed hypothesis is true. What it does not, explicitly does not tell you, is anything about whether or not the proposed hypothesis is correct, nor does it tell you anything about whether or not the data can be explained as being produced by random chance. The only thing that the p-value tells you is this thing above. Okay. However, despite that fact, the p-value is very, very widely used in the literature as a form or as a tool for hypothesis testing, or as a justification for whether or not the evidence, the experimental data that we have, agrees with or is in tension with the null hypothesis, that there is no underlying effect. And so we can, the reason that this happens, or the way in which this happens, is that we can basically say that we're willing to believe an effect, we're willing to believe that there is some underlying true effect in our data if the p-value has a value of alpha or less, where alpha is some probability, and you reject the idea that there is no underlying trend, no underlying effect present in your data if the p-value is less than some percent alpha. Okay? The probability that you accept that a hypothesis which is actually false, so given this choice that we've just made, that we say, I'm going to accept something as being in disagreement with the null hypothesis, provided it has a p-value less than 5%. The probability that you accept a truly false hypothesis, given that threshold, is alpha, is what this cutoff is, right? So you can consider the p-value as being the probability that you've accepted a false hypothesis, right? Now, in 1920, when Fisher first presented this idea, he proposed the use of p is less than 0.05 as an example, just an example, of a method that you might want to use as a method of exploring whether or not the data had any tension with the null hypothesis. Fisher very, very clearly believed that this should not be used alone. It should be used in the context of the wider experiment and things like that, the wider landscape of what we were doing. So I've described to you what the p-value is. Okay, I've given you an idea of how you can use the p-value in order to justify whether or not you think that your data follows the null hypothesis or is in disagreement with the null hypothesis. Given purely random measurement bias, what distribution do you think the p-value will take under many realizations of the same experiment? So if I make an experiment and I measure a p-value, and this experiment is governed purely by random noise in the sample, no systematic bias, no experimental error, nothing, just random noise driven by the sample that I've generated. And I run that simulation, I run that experiment many, many times. What distribution do you think the p-value, the distribution of p-values will take? Do you think it will be a distribution that peaks at a very, very small p-value and goes out to very, very high p-values with a lower probability? Do you think that it'll have some peak at 50% and it'll be some Gaussian around 50%? Do you expect that it'll be a uniform distribution between 0 and 1, so all p-values are equal? Or do you expect that it'll be an exponential which has a peak at 1 and a tail off to 0? Now recall that the way in which we justify whether or not a data set is in tension with the null hypothesis is if a p-value is less than some value. Okay, is whether a p-value is less than, say, 0.05. So what distribution do you think the p-value will take? under purely random noise. Okay, wait until we get a couple more responses. Okay, so we can do this test really simply. Okay, we can generate random data, random Gaussian data, and we can calculate the p-value. We can calculate the p-value, which is just because the standard deviation of this thing is 1. We can calculate the p-value as just being the absolute value of each observed data point, and the integral of the Gaussian PDF from the absolute value of the data point minus the integral to minus the absolute value of the data point. Okay. And when you calculate that histogram and you then put all the p-values into a histogram, this is what you get. So let's see how you did. Okay. So the overwhelming majority think that this will be a Gaussian with a center at 0.5 and some spread. In reality, the p-value takes the distribution of a uniform random variable between 0 and 1, which makes sense if we think about it first. So the p-value, we said, describes the fraction of samples that have a more extreme value than the one that we've observed, assuming the null hypothesis. If the null hypothesis is true, then we ought to see a value that is more outlying than the last 1% of the time, right? If we're sitting right in the middle, if we're at the mean, then we expect to see values that are more, that have a larger value 50% of the time, right? And so if I was to count the number of p-values that have a value a value which is greater than 50%, it'll be 50%. If I calculate the number of p-values that have a value less than 20%, it'll be 20%, because the probability of me finding a more extreme result if I'm 80% of the way to the edge of the distribution is 20%, right? And so what this means is that if every single scientist uses a threshold in this parameter to determine whether or not their results are significant, then they will get false positives n alpha % of the time, right? If every scientist were to use p is less than 0.05, what fraction of published data, what fraction of published science ought to be false positives? It's a relevant question, right? And it's one I'm going to ask you. So if every single scientist just used the threshold of p is less than 0.05 as a metric for determining whether or not their results were significantly different from the null hypothesis, and they use that threshold to decide whether or not to publish data, what fraction of actual published results in the literature will be false positives? So put down your guess or your feeling in the Slido. Hopefully nobody picks 100%, but I guess you could justify it. Okay, get a few more results in. This is a very, very relevant question. And it asks the question, how much published data is wrong? how much published science is just wrong, right? So let's assume that we're looking at an experiment, or rather a field, where there are 500 ongoing experiments, and all of them are exploring a particular possible physical relationship. Of those 500 experiments, 10% of them are real. 10% of those possible physical relationships are real underlying physical relationships. But of course, we don't know which are which. That's the reason we do the research. Okay. If every single physicist in this sample, or rather every single scientist in this sample, uses a metric of p is less than or equal to 0.05 as the determination for whether or not the effect that they are studying is real, and the researchers only publish when they find a significant result, what fraction of the results are wrong? This is the question we're asking. We can simulate this really simply. Okay, what we can do is we can simulate, I say 500 here, I've actually used 1,000 in practice, but anyway, it doesn't make a huge difference. So we can simulate 1,000 draws from a Gaussian where 50% of them are have real we can simulate, well, let's just actually do it in the pseudocode. So we can say that there's 10% of relationships in the analysis are real relationships. They have a real underlying effect, right? And the rest, the other 90%, are false relationships. They don't actually have any true underlying any underlying effect. They're just, they follow the null hypothesis. We can then ask the question of how many of the true relationships how many of the true relationships are accurately measured as having a real effect. Now, you can work under the assumption that if a true relationship is present, you ought to measure it a certain fraction of the time. Just given the fact that you have done an experiment, that experiment works, and it works 80% of the time. Okay, that value, how often, given a true relationship, do I expect to measure a true relationship? That's referred to as the statistical power of an experiment. Okay, and let's just assume, for the sake of argument at the moment, that statistical power is equal to 80%. So if you have a true relationship, if you have a true if your experiment is lucky enough to be exploring an actual true relationship between two things, then 80% of the time you'll get a positive result, a statistically significant result. What about the rest, though? What about all of the measurements that are being done on false relationships, on relationships that actually follow the null hypothesis? Right? Well, there is n times 1 minus the true fraction, so 90%. So n times 90% of those are actually measured, right? And let's just assume that those measurements are a Gaussian around 0, where 0 is the null hypothesis. We can then calculate the p-value for all of those measurements. And some of those measurements, by random chance, are going to satisfy the p-value threshold that we specify, 0.05. And if that's the case, that false relationship is lucky and gives a significant result, despite there being none there in reality. And we then crunch all this together into the total number of true measured relationships and false significantly measured relationships, and ask the question, what gets published? So if it's real, if there's a real distribution and the experiment was accurate, then it gets a significant result and goes to publication. If it's a real distribution, but the experiment was not accurate, it doesn't go to publication. If it's a false relationship, but it was lucky, it goes to publication. And if it was a false relationship and it was not lucky, it doesn't go to publication. And so we can use this simulation with just these numbers, the number of experiments being analyzed, the fraction of true relationships, the P threshold that we use for significance, and the statistical power of the experiments to figure out the fraction of false hypotheses that are published in the literature. And we run this experiment, and what we find is that 85% of the experiments had no effect, no true underlying effect. They followed the null hypothesis, and they didn't get a significant result. So those just end up in the trash. 5% have no true underlying effect, but find a significant result. These get published. There is 3%, 2% of effects that have a true underlying effect, but the result is not significant, so they end up in the trash as well. And finally, you have this 8% of truly existing relationships that also produce a significant result. Now, we're only interested in the things that actually make it to publication. And so if you ignore the things that end up in the trash, so the no results, this one and this one, then what you end up with is the fraction of published results that have no underlying effect, but get published as if they do. And it is 40%, given the set of observations, given the set of statistics and things that we have used. So because standard statistical practice is to only publish if you have a significant result, and because of the way in which the p-value has been constructed, and because there are more false hypotheses than true ones, if everything is working as it should, more than 1/3 of published results will be false positives based on p-values and success. Now, the standard expectation of people, as it is with you guys, is that if you are using a p-value of less than 0.05, that value should be 5%. It is not. It is much, much higher than 5%. And it's important to note that that is much higher than 5%, and we haven't even begun to start doing the dodgy stuff yet. And that's what we're going to be spending the majority of this lecture on, is the dodgy stuff. But it's based on these parameters. It's based on the statistical power. So how probable is it that an experiment is an experiment working with a true relationship will find it? It's related to the ratio of true to false hypotheses. So if there are many, many more false hypotheses than true ones, then this effect gets worse. And it's related to the significance threshold, the magic number that you select to justify whether or not your results are significantly different from the null hypothesis. If we have a particularly insightful set of researchers who only analyze hypotheses that are true 50% of the time, and their experiments are very, very well made, and so they have a statistical power of 95%, what does this look like? Well, in that circumstance, we get back down to about the 5%. So if academics are only working with hypotheses that are wrong 50% of the time, and their experiments are very, very well made, then we're at the level of P of less than 0.05 gives you about 0.05 false positives. But if, for example, researchers are incentivized to publish, which they are, and they're incentivized to explore large numbers of exotic hypotheses, which they are, and those hypotheses need to have less and less justification in terms of what we actually think might be realistic. These are things like exotic models. Then the fraction of true hypotheses might be very, very low as 1%. And if that's the case, then this value can be as high as 90%. false positives, right? And so this is a very significant effect, okay? This is a nice graphic from The Economist that I like, which kind of shows this in a more visual way for those of you who are more visually inclined. I won't go through it because we've got a lot to do and I want to keep going. But feel free to have a look at it in the lecture notes. Okay. This then brings us to the concept of like practical statistical inference. So what the whole point of this course is, right? So it's clear that if we use a p-value as a measure of significance, we end up with problems. We end up with problems that are related to how we select the p-value. It's related to how many hypotheses there are. In some fields, like in high energy physics, for example, there's a mantra of using a p-value that is much, much more restrictive than the 0.05 that we were using in the last slide. So if we were to use a p-value of say 0.001 and run exactly the same analysis that we just had, statistical power of 80% and 1,000 runs and 10% true hypotheses, then we end up with a much lower effect in terms of the number of false hypotheses that end up published in the literature. So why don't we just do that? Why don't we just set the p-value as having to be quite small and run with that? And the answer to that question is the problem is choice. The problem is that experiments don't happen in a vacuum without any sort of prior understanding of the people who are analyzing them. When we are analyzing a data set, our statistical analysis typically follows two steps. The first step is data mining, and the second step is data modeling. So the first step is where we explore and we summarize the data, and the second step is where we extract our model parameters and test our hypotheses. Each of those steps actually involves a number of sub-steps. So you have to define samples when you're data mining. You have to take your observations and you have to clean those observations of defective data, generally speaking. When you're modeling, you have to formulate a hypothesis, you have to construct your likelihood, we have to perform our inference, we have to decide how we're going to do our hypothesis testing, p-values or not, or whatever. And so what we're going to do for the remaining half of this lecture is explore some of the dangers that are inherent to all of these processes and how they can negatively affect the thing that we just spoke about with the p-value to be even more pathological than what we just saw. So while we could just go through and talk about how to do this well, how to do this right, it's much, much more educational in my mind to do the opposite. It's much, much more interesting and much, much more fun for us to go through and talk about bad statistics, how you can do this in a bad way in order to hack your way to significant results and why that happens, how it happens, and that way you can know what to avoid. Please do not take this as a how-to guide, take this as a how not to guide. So what we're going to talk about in terms of our bad statistics is we're going to focus on a couple of effects or a couple of ways that you can modify, or rather that you can go about your statistical analysis that are going to pathologically influence your conclusions, pathologically bias the results that you measure and the models that you infer. We're going to completely ignore the case of spurious correlations. Now, we spoke about spurious correlations earlier in the course. Spurious correlations make this exponentially more difficult because no longer do you just have to worry about things that we're going to be talking about. You have to worry about the combinations of different variables in the background and how they play in with one another. So this is almost a best case scenario. It's also almost a best case scenario because we're going to look at these things one at a time. And in reality, if you were to combine these bad practices, you can hack your way to very, very significant results very, very easily. And we'll see how that happens. So we're going to start off talking about variable selection. So scientists working with a particular set of observations will generally have a large number of variables that they measure. So let's make a let's make a data set. Our data set contains 100 observations, which they could be galaxies, they could be particle collision measurements or whatever. And it has 100 different observations in 20 variables, which I'm only showing 7 of them here because they drop off below the bottom to here, et cetera, et cetera. Okay, so this is what our data looks like. We've got variables 1 through 20, and we have 100 observations of each. We have some theoretical expectation that each one of these variables ought to be centered on 0. Okay, makes our life easy. Let's say that that's the null hypothesis, is always that the value, the true value of these parameters is 0. And we want to compare how our data differs from the null hypothesis using a t-test, that thing that we spoke about a few slides earlier. So let's take the first variable. Just have a look at the first variable. It's got a minimum of -3, a maximum of 2 and a bit, a mean of 0.03, da, 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 da. Let's run our t-test. So we run our student t-test to calculate the significance of this variable with respect to the null hypothesis. The null hypothesis being that the true mean is equal to 0, the alternative hypothesis being that it is not equal to 0. And we calculate our t-value given the degrees of freedom, and that gives us a p-value. And our p-value for the first variable is 0.75. So very, very much larger than the threshold of 0.05. So nothing significant there. And we go, okay, nothing significant there. What about the second variable? We do the same game. We get a p-value of 0.3. Nothing there either. Let's go, keep going. We go to the fourth variable, nothing there. We go to the 9th variable, nothing there. We go to the 14th variable, nothing there. We go to the 17th variable, hello. In the 17th variable, we find a p-value of 0.008. Highly, highly significant with respect to our threshold of 0.05. So we found a significant relationship that says that the 17th variable is discrepant from the null hypothesis with a value of 0.0085. We write up this discovery, publish the results, and the discovery is enshrined in the literature forever. What is the problem with that? The process that we've just described is known as data dredging, or the look elsewhere effect, or the problem of multiple comparisons, depending on whether or not you're a machine learning person, scientist, arguably, or statistician, basically where those 3 different terms come from. The core issue here is that the threshold that we calculated, the p of less than 0.05, is designed for comparing one set of observations with the hypothesis, with in this case, the null hypothesis. And it doesn't take into account the fact that we looked at one variable and found nothing, and then went, well, instead I'm going to look elsewhere. I'm going to look at a different variable, and I move over and I check over here. Remember that we said that the p-value for many experiments looks like a top hat, looks like a uniform distribution from 0 to 1. If I find one variable that has a p-value of 50, and I go, okay, don't care about that one. I then find another that has 0.8, another that has 0.2, another that has 0.9, another that has 0.5, and then all of a sudden I found one that has 0.02, and then I say, aha, significance, right? Given this flat distribution and a p-value threshold of 0.05, I should, from random fluctuations alone, find a p-value less than 0.05 in 1 out of every 20 observations. If I have 20 variables that I'm analyzing, I am very likely to find at least one that satisfies the p-value test against the null hypothesis just from random chance. Okay? And so it's very easy to find a significant, in inverted commas, variable. Now, one can correct for this analysis, for this problem, using something that's using basically a sliding window for the value of the threshold that I care about. Basically modifying my P is less than 0.05 in order to account for the fact that I've looked elsewhere. And the simplest example of a correction like that is called the Bonferroni correction. And that basically just says that for m different variables that you have looked at, your threshold should be whatever the initial threshold was, alpha, so in our case 0.05, divided by m. Okay, so if I observe 5 different variables, my threshold should be 0.05 divided by 5. If I observe 20, it should be 0.05 divided by 20. And so there's actually lots of different ways that you can do these corrections. And I'm showing you a couple of them here in the literature. Sorry, in R, the box has been truncated here. I'll fix that. But the dashed red line that you can see here is actually the no correction to my p-values. And so I have some p-values that have a p of less than 0.05, and that was variable 17. That's what I found, my variable 17. And I said, that's significant, I'm going to publish. But if I account for the fact that I have 20 variables using a whole host of different possible ways of correcting them, which are named after these people, the Bonferroni is this one here, the blue dash, then what you can see is that if I make those corrections, all of a sudden there is no observation that is less than 0.05. And so none of my observations are significant anymore. This is a really important effect, and it's a very important effect, more so than just having many different variables. This can happen with any data set where you have a large number of observations. Okay, and in the modern big data environment that we all work in, this is a huge issue. And there's a really excellent, possibly my favorite scientific study of all time, is what we're about to discuss next. And that is the experiment to discover if fish show empathy. There was a question posed by a group of researchers who work in functional magnetic resonance imaging, fMRI, in 2009. The researchers proposed that they could use fMRI to determine whether or not a fish would show activity in its brain when showed pictures of humans as opposed to pictures of inanimate objects, chairs, tables, etc. And so they took an Atlantic salmon and they put the Atlantic salmon in an fMRI machine. And then while it was in the fMRI, they showed the salmon pictures of people and pictures of inanimate objects. And they scanned the fish, scanned its brain while they were going through and saying, this is a picture of humans, this is a picture of a chair, this is a picture of such and such. And afterwards, they analyzed the fMRI data and they found a, many sigma significant detection of activity in the salmon's brain that correlated with when it was being showed a picture of people. And so at many sigma significance, the fish was showing empathy with people because it reacted specifically when it saw humans. The problem? The salmon was frozen at the time of the study. It was a whole Atlantic salmon that had been bought from a butcher and was frozen solid. And this whole experiment was designed as a demonstration that because fMRI studies present the scientists with tens of thousands of possible observations every time they are run, it is extremely easy to construct significant events that correlate with what you're looking for from random fluctuations alone. This is a greater than 4.5 or greater than 3 sigma observation that is exactly in the middle of a salmon's frozen brain when they were showing particular pictures of humans and inanimate objects. This study is excellent, and you should definitely find. You can read this poster from a conference that actually describes this experiment. But the purpose of this experiment was to argue for implementing in fMRI studies a multiple comparisons correction. And the multiple comparisons correction is this thing here. So they were working with the red dotted line, and they're essentially saying that that is very, very dangerous, and therefore we should be using multiple comparison corrections in order to stop this from happening. My favorite scientific study of all time. The next problematic activity that one can do in order to produce something which is reasonable or rather significant is data modification. So data modification can take a whole different bunch of numbers of forms, and it doesn't necessarily have to be malicious. It doesn't have to be intentional. It can be accidental, right? But it's a very important effect. At its very most benign, most innocent, data modification happens because we discard things that we assume are outliers. So when we're going through the data analysis process, we identify parts of the data that we say are outliers. They don't agree with the rest of the data set, and therefore they should be discarded. At its most malicious, it involves hand-picking parts of the data that satisfy and suit your hypothesis. That process, or rather both of these processes, even when they're completely unintentional and innocent, are referred to as cherry-picking data. We can demonstrate cherry-picking really, really easily. Okay, we can generate a data set, and we can say that we have a strict requirement, p-value of less than 0.01, and we can say and we can assume that this is the only variable that we're analyzing, and so we don't have to worry about any of these multiple variable corrections. And we look at our data, and our data looks like this. Now, if by eye we look at this data and we say, okay, the mean's probably over here. I know that my null hypothesis is 0, and given the range of the data, yeah, I mean these two observations here look like they might be outliers. Now, if I compute a p-value here of this particular data set, I find that my p-value is 0.07. And I'm a researcher who wants to publish. I can convince myself I'm so close to a result, and that data point there looks a bit dodgy, looks like it might be an outlier. What happens if I get rid of that outlier data point? Just that one data point. There's 100 observations here. It's 1% of the data. How much can it really matter? Really? And so we get rid of that one data point. It's only 1% of the data. What happens to our p-value? Well, we drop below the 0.05. Okay, we drop below our 0.05 threshold, and we go, okay, 0.05, that's enough. I'm going to go off to the journal. We take this and we run with it. It's extremely easy for researchers to fall into the process of inadvertently cherry picking because of outliers in data. Experimental data is messy, right? And so it's easy to fool ourselves into thinking that we have some truly bad data when in fact we just have a random fluctuation. The crucial point is that removing that data point has a much larger effect on something like the p-value than the 1% data that you would naturally apply to it given the number of observations in the data set, specifically because you've picked the thing that is most discrepant, rightly or wrongly. Right? And so it's very, very difficult. That's the innocent version. That's the innocent version of cherry picking. People working with data, cleaning their data, thinking that they're producing a more reliable data set, and inadvertently producing significant results where there is none. The malicious version of cherry picking is the real world example that I'm going to talk to you about, which is climate denying. It is extremely common in climate denialism for people to cherry pick observations that suit their hypothesis. And there's a very, very easy demonstration of this in a newspaper article in 2011, which claimed that the National Snow and Ice Data Center records show conclusively that in April of 2009, Arctic sea ice extent had returned to and surpassed the levels of 1989. Now the implication of that statement is that there's no cause for alarm. There's no worries that we have with climate change because there is no systematic reduction in sea ice because the observations in April of 2009 were in excess to what we observed in 1989. Okay? And therefore, that you are taking that data point as a demonstration that there hasn't been a systematic reduction in sea ice between those 2 years. That may be a fair line of argument, unless they've done something to very specifically identify a data point that fits their hypothesis that doesn't fit the global trend. Looking at the data that they actually used for that argument, this is the data. That is April 2009, and that difference is the difference to which they're referring. The sea ice in April of 2009 extended to, was in excess of the values in 1989, and therefore there is nothing to worry about. Whereas naturally, if you were to take any other statistic, literally any other statistic that you could possibly conceive between these two lines, you would come to the conclusion that the inverse is true, that there has been a reduction in sea ice between 2009 and 1989, right? If you were to take the mean of these two graphs, 2009 would be lower. If you were to take the median, it would be lower. If you were to take the modal difference between the two, it would be lower, right? There is no statistic that you could construct except for that one data point, singling out that one data point, that would give you the conclusion that they are interested in. And so that's what they did. They singled out that one data point. And that is the essence of cherry picking. Okay? Cherry picking, bad. It's particularly bad in this case, but it's also detrimental when it's unintentional. Okay, the next possible problem is what we're going to refer to as additional observations. And this is a really important one. You get a significant statistical fallacy in significance estimation because of the way in which we as scientists collect data. Let's consider an experiment where we make n observations of some variable x, and we compute our statistic of choice using, let's say, the t-test, and we calculate a p-value. That p-value that we measure is right on the cusp of being significant. It's not there, but it's really close. And so we therefore decide that we're going to take some additional data. And the reason that we take the additional data is because if there is a true underlying relationship, that additional data will increase the discrepancy with regards to the null hypothesis, will push us over the p-value line, and we can be confident that our result is real. We take the data, we find that the p-value drops below our threshold, and we publish. What's the problem with that process? Well, again, this is something that we can simulate pretty easily. So we can construct n observations and we can compute a p-value, and our p-value is right on the threshold. This is the same data that we just drew on the last slide. We can then say, all right, let's observe 10 more observations. We observe our 10 more observations, and all of a sudden the p-value drops down to 0.02, below our 0.05 threshold, and we go, bingo, we've satisfied the 0.05 threshold, and we can run to the publisher. What happens if we were to keep observing data? Well, what we find is that if we keep observing data, we cross the p-value threshold. That was the threshold that we just crossed just there, right? Or sorry, rather, we were at 100, and then we've observed another 10 data points. So we drop there, and we observe a bit more data, and it drops back across the line. We go, okay, we observe a little bit more, and we sort of dance on the threshold. And then once you get to 200, 190, 200 observations, the p-value overwhelmingly digresses back towards nothing significant. This effect of taking more data until you find a statistically significant result is referred to as p-hacking. That term actually can be used to describe a bunch of the statistics, a bunch of the effects that we're talking about here. Basically, anything where you modify the data or the experiment in some way in order to get a statistically significant p-value can be called p-hacking. So technically, all of this can be called p-hacking. But this effect in particular of taking more data is one of the main ways that people p-hack. The problem comes about because we make a decision when to stop. The decision that we make is when we stop taking data because we have satisfied some arbitrary threshold, right? One can then ask the question, if I was to perform this process, so if I take 100 observations and I calculate the p-value and I say, is it significant? And if it isn't significant, I take another 10 data points. And I do that until I have a maximum of 1,000 observations. How many of those, or how often rather, given that method of starting with 100 observations and then adding 10 and 10 and 10 and 10 and 10, how often do I expect that process to allow me to cross the statistically significant threshold, given truly null hypothesis data? And the answer is around 30% of the time using this setup. So given absolutely no effect, just by taking sequentially small chunks of data and checking the p-value every time, I can guarantee that I'm going to find a significant result in a single variable 30% of the time. And again, if my interest is to publish, then why wouldn't I do this? Right? Given a statistical significance threshold of 0.05. Okay, so this is another significant problem. And this happens. This happens quite frequently. Every time you see someone that says that we weren't quite sure, so we took some more observations, this is a problem. The last statistical fallacy that we're going to talk about is to do with the human brain, which is to do with how we consciously or subconsciously influence the measurements that we make. And this is, again, because, as I said at the beginning, experiments don't happen in a windowless room without any idea of what's going on in the foreground. They're done by human people working in laboratories, generally who have a long history of working in the field, right? And that context is important. Now, when we discussed Bayesian statistics, we spoke about how this prior knowledge was actually a good thing. We spoke about how having a prior on a particular parameter allows you to create an informative prior and get better posterior inference. But the prior knowledge also has a dark side, and that dark side is the way in which we subconsciously or otherwise want to be consistent with previous work. And that leads to a concept which is very important, which is known as confirmation bias. Confirmation bias is very, very prevalent in the natural sciences. You can see it in lots and lots of different experiments. You can see it in lots of different fields of the natural sciences. But one or two rather really nice observations or examples of it. One is in the value of this parameter eta plus minus, which is to do with the coefficient of charge parity violation in particle physics. If you look at the value of this estimated parameter prior to 1973, every single observation, every single experiment found the same value to a very, very significant level. The mean of these observations has an uncertainty on it that is extremely small. But after 1973, something happened. What that something is, I personally don't know. My guess is that a new experiment came online. That's generally what happens. And all of a sudden, the data sets jumped, the values jumped, and they moved to a totally different value, totally different part of the parameter space, and again, started to all have very similar values. And this is the essence of confirmation bias. These researchers had an expectation of their result, and they found that expectation. That expectation then changed, and again, the new researchers found that expectation. This effect is present in early estimates of the speed of light. It's present in early estimates of cosmology. The value of the Hubble constant determined by Edwin Hubble is wrong. And the reason is because of confirmation bias. Well, right, I've already said that. However, you might have the tendency of thinking that, okay, all of this is only related to when we have a p-value or something of 0.05, or it's only relevant for the natural, for the social sciences or stuff like that, because in my analysis, I use a p-value of 0.000001, and I ensure that there's absolutely no way that I can get any statistical anomalies. And I'm very careful with my research, and therefore I don't fall into these traps. An excellent example of how this occurs in physics and in astronomy is the existence of the pentaquark. So in 2002, a Japanese lab found an exotic baryon that was made up of 5 quarks, not the usual 3. Okay, and it's called the theta plus pentaquark. And they found it at greater than 5 sigma significance, 1 chance in 20 million of it being a false positive. After that, in 2003, 2004, 11 independent research groups looked for and found at 4 to 8 sigma significance evidence for the theta plus pentaquark in different independent analyses. However, since then, in 2006, 2007, 2008, all the way through till now, more experiments with more statistical power performed the same experiment and found nothing. And the reason for this false detection is because the researchers involved in finding all of these, the first one and the subsequent reanalyses, weren't blind to their data. They knew what they were looking for and they found it. And this is confirmation bias. Okay. There are actually, in fact, still arguments as to whether or not the theta plus pentaquark is real. It's an ongoing discussion in the particle physics literature. But the underlying facts are that if you are not blind to your data, if you are not blinded to your analysis, then you are very likely to run into problems with confirmation bias. And as a result, lots of fields are particularly working quite hard to ensure that analyses are done blinded. What that means is that the methods of determining or rather the methods of doing the statistical analysis are finalized on data that is not the real data, or rather that is a modification of the real data, that therefore means that your final value doesn't make is not meaningful. And only once the methods are frozen is the data unblinded, basically converted back to its true form, and the analysis is run. Parameters are inferred, like the value of the Hubble constant or the value of the matter density parameter in cosmology, or whether or not there is a theta plus pentaquark at a particular energy level. And that analysis is then published, agnostic to whether or not it satisfies some significance. Okay. And that is the essence of a blinded analysis. And it's very, very important to avoid confirmation bias. Cool. Right. So that's the set of different statistical problems or bad statistical practices that I spoke about, that I decided I thought were the most relevant to discuss this lecture. There are a few very important ones that I didn't mention. I'm conscious of spending the last 15 minutes of this lecture giving you the ability to do the lecture feedback. So I don't want to use up too much more time, but these are very, very interesting in their own right. Very, very briefly, I can describe them. Regression to the mean refers to the problem of defining a sample to analyze based on a noisy quantity. And so if I have a variable that I use to define my sample, and it's a random variable that has some distribution, call it a Gaussian, and I define one sample to be the sources in that end, and I define another sample to be the sources in that end, and then I remeasure a new experiment with these variables. Okay? Because of random noise, I expect the average of this population to move towards the mean. And I expect the average of this population to move towards the mean. And therefore, I can fool myself into thinking that there has been a statistical effect when in fact there isn't. It's just the difference between random realizations of one data set and another based on the fact that I made a very biased selection in the first place. And this is very significant, particularly in medical sciences, because when you're selecting a group to trial, for example, a new cholesterol drug on, you don't pick normal, healthy people. You pick people who need cholesterol medication, right? And if they then move towards the mean after taking the drug, you need to know whether or not that is statistically significant or whether they've just regressed towards the mean because of random fluctuations. And that's the reason that you always, in medical surveys and things like that, have a control group drawn from the same biased initial population, but not given the thing that you're trying to treat. Because what happens is both the treated group and the control group regress towards the mean. But if the treated group regresses more, then you have an effect. So this is the basics of regression to the mean. We spoke about spurious correlation. The last one is another really interesting one, which is called survivor bias. Survivor bias is most well known for an effect during the Second World War, where you're going to have to indulge my terrible drawing of an aeroplane here. Oh, it's not too bad, actually. There you go. There's my terrible drawing of an airplane. And one of the classic example of survivor bias is in World War II, they were trying to figure out where they should reinforce airplanes because of damage. And what they found was that planes preferentially had bullet holes on the wings and on the tail. And they therefore said that it is in our interests to reinforce these sections of the aeroplane because those are the sections of the aeroplane that get hit the most. And there is a significant problem with that analysis. And that problem is what's called survivor bias. And what that means is that the sample that you are analyzing in order to do your inference is a very heavily biased sample. And in this circumstance, it's heavily biased because these are the planes that made it home. In reality, the places that you want to shield are the places that don't have the bullet holes, because the bullet holes on the planes that return home survived getting shot in those places. The planes that you don't see, the ones that were shot down, were the ones that were struck in this region. And therefore, that's the place you actually want to put your reinforcement. And so this is a demonstration of survivor bias. And this is, the most famous example. Okay, feel free to have a read of those different effects. I really do recommend going and having a look at these different things on your own time. There's lots of there's lots of popular literature as well as statistics literature on all of these different things. And a lot of these particular effects are very well known nowadays and are becoming more and more well known. And indeed, the use of the p-value is becoming less and less widely used because of all of these problems that I've just spoken about. And if I was to give you one piece of advice, it would be skeptical of any analysis that uses a single threshold on a p-value as a determination of whether or not something is significant. Because even Fisher in 1920 said that that wasn't the right thing to do. The p-value is not a tool for unilateral decision-making. It is a tool for assisting in inference. Cool. So that's where we are. That's the end of today's lecture. That's my template. So we're going to now have 15 minutes, or rather 10 minutes, for you guys to fill out the dedicated time for you to fill out the lecture evaluation. It's all totally anonymous. You should have received in your email inboxes a link. And I think that you'll find that that link was actually sent twice. Once there was a problem with the links, and then they were sent again. So if you do check, please check that you have the correct link. And I just would really like to spend the time, take this 10 minutes for you to give you the opportunity to go and fill out that evaluation. That evaluation is particularly useful for me because, as you know, this is the first time I've ever given this lecture course, and it really will be very useful for me to have your feedback. So please give your feedback. And if you have any questions, of course, feel free to ask them either on the Slido or now live. I'll stop the recording and we can have 10 minutes just chatting or whatever you would like.